Have you ever spent 45 minutes scrolling through Netflix, watching absolutely nothing, until you're too tired to care anymore? Or maybe you know that specific anxiety of driving around a crowded parking lot, wondering if you should take the spot you just saw, even though it's a 5-minute walk from the entrance, or risk driving closer, hoping for a miracle, but potentially ending up with nothing. If you have, you're not indecisive. You're just facing a computational problem with limited resources. We often treat these moments of decision paralysis as personal failings, like if we were just more organized or decisive, we wouldn't struggle. But the truth is, these are mathematical challenges that even supercomputers struggle with.
The constraints of daily life, finite time, limited space, incomplete information, are the exact same constraints computer scientists have been grappling with for decades. And the solutions they found? They're actually applicable to being human. That is the core premise of Algorithms to Live By, a fascinating exploration by Brian Christian and Tom Griffiths. They argue that the algorithms used by computers to sort data, schedule tasks, and manage memory can actually serve as a blueprint for how we live our lives. It turns out there is a provably optimal way to buy a house, a mathematically sound strategy for organizing your closet, and yes, even a correct method for deciding when to stop looking for a parking spot.
In this series, we are going to decode these strategies. We're going to look at how computer science can help us forgive ourselves for being human, and how to make better decisions with less anxiety. To start, we need to tackle the biggest question of them all. When do you stop looking and start committing? It's a problem computer scientists call optimal stopping, and the answer might surprise you.
Welcome to The Last Read, books for your ears, wisdom for your life. If you enjoy these deep dives, go ahead and hit that subscribe button now, so you never miss a chapter. Now, imagine for a moment that the anxiety you feel when making a decision isn't a personality flaw. What if it's just a debugging error? What if computer science actually solved your daily stress decades ago and nobody bothered to tell you? This book, Algorithms to Live By, posits that the exact same logic computers use to manage data can help us manage our messy human lives, and they are precise about it.
For instance, there is a magic number for commitment. It's 37%. Whether you are looking for the one on a dating app or trying to find a house before your lease runs out, the math says there is a specific, calculable moment when you should stop looking and start settling. It's called the secretary problem in computer science, and it suggests there is a proven mathematical limit to how much shopping around you should do. And it's not just about big commitments. Have you ever started a new hobby, maybe knitting or learning Italian, and wondered if you should push through the frustration or just give up? There is an algorithm for that too. It's called the Explore-Exploit trade-off. It gives you a literal formula for when to stick with the tried and true and when to take a risk on something new. We aren't talking about vague self-help advice here. We are talking about provable, optimal strategies for living. In the coming episodes, we are going to hand you these cheat codes. But before we can run the program, we need to meet the programmers. Who exactly figured out that the secret to being a better human is thinking like a machine? So, who are the people audacious enough to claim that your brain should run more like a hard drive? On one side, we have Brian Christian, and he is a bit of a paradox himself. He holds degrees in computer science and philosophy, but he also has a Master of Fine Arts in poetry. Think about that for a second. A man who speaks fluent C++ and fluent stanza. He is the author of The Most Human Human, a bestseller that explores what artificial intelligence can teach us about being alive. Then you have Tom Griffiths. Tom is a professor of psychology and computer science, currently directing the Computational Cognitive Science Lab at Princeton. His entire career has been dedicated to a single fascinating question: how do we make decisions?
while Brian looks at the poetry in the code. Tom looks at the math in the mind.
Together, they are the perfect storm, a poet-programmer and a cognitive scientist. When they sat down to write algorithms to live by, they weren't trying to turn us into unfeeling robots. Quite the opposite. They realized that computers deal with the exact same constraints we do: limited space, limited time, and incomplete information. They saw that the messy human problems, like trying to find a spouse or organizing a chaotic closet, are actually distinct mathematical problems that machines solved a long time ago. They didn't just write a tech book. They wrote a guide to being human in an increasingly complex world. They argue that intuition isn't magic. It's just an algorithm we haven't learned to calculate yet. And the first calculation they want to teach us is perhaps the most famous one in the book. It addresses a universal anxiety, the fear that if you settle down now, you might miss out on something better later. But if you keep looking too long, you might end up with nothing at all. Whether you are looking for a parking spot at the mall or a partner for life, the math says there is an exact moment you should stop looking.
And that exact moment is essentially the solution to what mathematicians call the secretary problem, though you might find it more relatable as the dating dilemma. Imagine you're trying to hire the best assistant or find the perfect partner. The catch is, you see candidates one by one, and once you reject someone, you can't go back. If you pick the first person, you have no benchmark. They could be the worst option, and you'd never know. But if you wait until the very last person to compare everyone, you're forced to settle for whoever is left, even if the best person walked out the door an hour ago. This is the classic case of optimal stopping. It's that paralysis of not knowing when to pull the trigger.
Christian and Griffiths explain that the mathematically proven strategy is something called the 37% rule. The logic is surprisingly simple. You should spend the first 37% of your search time or the first 37% of your candidates just gathering data. You look, you evaluate, but you do not commit. You are strictly setting a baseline. Once that 37% phase is over, you immediately choose the very next option that is better than everything you've seen so far. Think about it like looking for a parking spot at a crowded mall during the holidays. You enter the lane. Do you take the first spot you see, miles away from the entrance? Probably not. But do you drive all the way to the front, risking that there are 0 spots left and you have to awkwardly circle back? Also risky. Optimal stopping tells you exactly how far to drive. You pass a certain percentage of spots to gauge how full the lot is. That's your data gathering. Then, the moment you see a spot that's better than the ones you passed, you take it. You don't keep looking for the perfect spot right in front of the door. You stop.
The math gives you permission to stop worrying that something better is around the corner. It tells you that by following this rule, you have maximized your probability of the best outcome. You're not settling, you're optimizing. But this rule assumes you're looking for one best thing to commit to forever. What about the smaller choices we make every day? Like, should you go to your favorite burger joint for dinner tonight or risk trying that new fusion place that just opened up across town? That is a completely different type of mathematical headache, one that involves balancing the comfort of the known with the potential of the unknown. And the answer depends entirely on how much time you have left on the clock. One that involves balancing the comfort of the known with the potential of the unknown. And the answer depends entirely on how much time you have left on the clock. This is the classic explore versus exploit trade-off. It sounds technical, but you play this game every single time you open a food delivery app. Let's stick with that dinner dilemma. You have two choices. Option A is your favorite burger joint. You know the menu by heart, you know exactly how good the fries are. That is exploitation. In computer science, that doesn't mean taking advantage of someone. It just means using the information you already have to get a guaranteed good result. Option B is that new fusion place across town. It might be amazing, it might change your life, or it might give you food poisoning. That is exploration. You are gathering new data, but you're risking a bad experience to do it. So how do you decide? The book says you have to look at your time horizon.
Imagine you just moved to a new city where you plan to live for 10 years. In this scenario, you should be exploring like crazy. Try the fusion place. Try the terrible dive bar. Even a bad meal is valuable data because it tells you where not to go for the next decade. The value of information is high because you have a long time to use it. Now, flip the script. Imagine it is your very last night in that city before you move away forever. Do you risk the new place? Absolutely not. You go to your favorite burger joint. You exploit the knowledge you have to ensure your final experience is a great one. There is no point in gathering new data if you have no time left to use it. This actually explains the entire arc of human life. Think about babies. They are pure exploration machines. They put everything in their mouths. They are constantly testing boundaries. They are gathering data because they have a massive time horizon ahead of them.
Then look at the elderly. We often say older people are set in their ways, as if that's a bad thing. But mathematically, they are being perfectly rational. If you've spent 80 years figuring out exactly which coffee you like and who your favorite friends are, and you know your time is limited, why would you waste an afternoon on a bad cup of coffee with a stranger? You wouldn't. You exploit the best of what you found. So, if you feel like you're becoming more boring as you get older, don't worry. You're just optimizing for your remaining interval. But speaking of optimization, we usually assume that being organized means having a clean, spotless workspace. But what if I told you that a messy desk, the kind with piles of paper everywhere, might actually be the most efficient system of all? It turns out your computer manages its memory the exact same way you manage that pile of clothes on your chair, and it all comes down to something called caching.
Now, we usually think of organization as everything being perfectly sorted, alphabetized folders, color-coded labels, a place for everything and everything in its place. But computer science actually challenges that. It says sorting is expensive. It takes time to file things away. And unless you are going to search for those exact papers over and over again, that time is often wasted. Instead, computers rely on caches. Think of a cache as a small VIP section of memory that is super fast to access. Your computer has a massive hard drive. That's like a library basement. It can hold everything, but it takes a while to go down there and find a book. Then it has the cache. That's the book you have open on the desk right in front of you. The golden rule of caching is simple. Keep the things you use most often in the fastest, most accessible place. And the best way to do that? The least recently used algorithm, or LRU.
It sounds fancy, but you probably already do it in your closet. Picture your wardrobe. You have the clothes on the hangers, easy to grab. Then, maybe you have a box in the attic or the garage. The least recently used rule says that when you need space in your closet for a new jacket, you shouldn't just throw out a random shirt. You should evict the item you haven't worn in the longest time. That plaid vest from the 90s? It goes to the attic, the slow memory. The jacket you wear every day stays on the hook, the fast cache. And this brings us back to that messy desk. There's a Japanese economist named Yukio Noguchi who invented a filing system that looks remarkably like a mess. He put all his files in a row in a cardboard box. Every time he used a file, he'd put it back on the far left side. Over time, the files he used most often naturally floated to the left, right where he could reach them. The files he never used drifted to the right. He didn't waste hours alphabetizing. The system organized itself based on usage.
So, that pile of papers on your desk, the document you need right now is probably right on top. The one you needed yesterday is just under it. The paper at the bottom of the stack, you can probably throw it away and you wouldn't even notice. That pile isn't a mess. It's a perfectly optimized LRU cache. But there is a catch. While keeping your most active projects right in front of you is efficient for access, it can be dangerous for focus. Because when you have too many active files open on your mental desktop, you start jumping between them. You answer an email, then check a notification, then write a sentence, then check the email again. In computer science, this constant switching has a name, and it's a productivity killer. It's called thrashing, and it happens when you spend more time managing your tasks than actually doing them.
Thrashing. It sounds violent, and honestly, it feels violent. In computer science, thrashing happens when a computer runs out of fast memory, your RAM, and has to start using the hard drive to store active programs. The problem is the hard drive is slow, so the computer moves a bit of data from the drive to the RAM, does a tiny bit of work, realizes it needs different data, moves that first chunk back to the drive, and pulls the new stuff in. It's called paging, and it takes time. If the computer has too many tasks open, it eventually reaches a point where it is spending 100% of its energy moving data back and forth, and 0% of its energy actually running programs. The system grinds to a complete halt. It's working harder than ever, but accomplishing absolutely nothing. Does that sound familiar? It's that feeling on a Tuesday afternoon when you have 15 tabs open, 3 unread Slack messages, an email half written, and a phone ringing. You stop writing the email to answer the phone, but then you see the Slack message, so you hang up and start typing a reply, but then you remember the email, and suddenly 20 minutes have passed, and you haven't finished a single sentence.
That is human thrashing. The book Algorithms to Live By points out that the real killer here is context switching. Every time you switch tasks, there is a loading time for your brain to get the right information into your working memory. If you switch too often, you are perpetually stuck in that loading time. So, what is the algorithmic solution to thrashing? You might think you need a better prioritization system. You might think, I need to sit down and list every task, weigh its importance against its duration, and calculate the optimal sequence. No, do not do that. When a computer is thrashing, the last thing it has the resources to do is run a complex prioritization algorithm. That just adds more load. The book suggests that when you feel that sense of overwhelm kicking in, you need to stop prioritizing entirely. The best algorithm for a thrashing system is one that requires zero mental overhead.
Go with first in, first out. Just do the very first task that landed on your desk and ignore the rest until it's done. Or use earliest due date. Just do the thing that is due soonest. It doesn't matter if it's the most important strategic move for your company. Right now, your goal isn't strategy. Your goal is to stop the bleeding. By picking a rule that requires no thinking, like do the top paper on the pile, you eliminate the meta work of choosing. You stop the context switching, and you actually start processing again. Sometimes the smartest move is to stop trying to be smart and just be simple. And this tension between trying to have a perfect, complex model of the world versus a simple, robust one leads us to one of the biggest dangers in both data science and daily life. It's a trap where trying to be too precise actually makes you wrong. It's called overfitting, and it might be the reason your perfectionism is holding you back.
Which basically means you're seeing patterns that aren't actually there. In data science, overfitting happens when you create a model that fits your past data a little too perfectly. You tweak it, you add more variables, and you make it complex enough to account for every single blip and anomaly in the history books. It explains the past with 100% accuracy, but when you try to use it to predict the future, it fails miserably. Why? Because it didn't just learn the signal, it learned the noise. It memorized the random luck and the flukes, thinking they were permanent rules. And this is a profound insight for anyone who struggles with anxiety or perfectionism. Think about when you're agonizing over a big decision, like choosing a partner or a career path, or even just buying a house. You try to factor in everything: interest rates, school districts, commute times, the color of the kitchen cabinets, that one weird comment the neighbor made. You build this massive, complex mental model to guarantee you make the perfect choice.
But the book argues that this complexity is actually dangerous. As the authors put it, the greater the uncertainty, the more you should prefer simplicity. When you try to account for every variable, you end up overfitting to your current fears and circumstances. You're trying to fit the noise. And just like a computer model that's too complex, a human brain that is overanalyzing is fragile. It breaks the moment the future doesn't look exactly like the past. The solution in computer science is something called regularization. It's a fancy term that basically means penalize complexity. You deliberately stop yourself from thinking too hard. You force yourself to use a simpler rule, even if it feels less precise.
There's a great line in the book that sums this up. Don't always consider all your options. It sounds counterintuitive, right? We're taught to look at every angle. But often, looking at just one or two critical factors and ignoring the rest actually leads to better results because it's more robust. It handles the chaos of the real world better than a delicate, perfect plan. So, if you're drowning in data, stop. Don't try to build a perfect map of the world. Just use a compass. And once you embrace this idea, that simpler constraints can actually be a relief, you start to realize that you can offer that same relief to the people around you. It turns out, being vague isn't always polite. Sometimes the kindest thing you can do for someone else is to make the decision for them. This brings us to a concept called computational kindness, and it might change the way you schedule your next dinner date.
Which leads us directly to the concept of computational kindness. We've all been there. You want to set up dinner with a friend, so you send a text, "When are you free?" You think you're being polite, right? You're being flexible, you're accommodating, but actually, you're being a bit of a burden. In computer science terms, you've just handed your friend a massive search problem. They have to scan their entire calendar, weigh every possible slot against their energy levels, their other commitments, their commute. It's exhausting. The book argues that this polite vagueness has a, quote, dark computational underbelly. By declining to state a preference, you aren't being nice. You're passing the cognitive buck. You're forcing them to do the hard work of calculation. Computational kindness is the antidote. It's about recognizing that everyone's processing power is limited. Instead of asking, when works for you, you say, how about Tuesday at 7 or Wednesday at 6?
Suddenly, you've turned a complex search algorithm into a simple verification task. All they have to do is check 2 slots, yes or no. It's faster, it's easier, and ironically, it's much more polite. And this really gets to the heart of what Algorithms to Live By is all about. Throughout this series, we've talked about sorting, stopping, and scheduling. It's easy to think of these as tools to make us more machine-like, more efficient, cold, and calculated. But the authors, Brian Christian and Tom Griffiths, leave us with the exact opposite conclusion. Using algorithms isn't about becoming a robot, it's about forgiving ourselves for being human. Computers have shown us that even with infinite processing power, some problems simply cannot be solved perfectly. The traveling salesman problem, the scheduling conflicts, they are mathematically impossible to optimize in a reasonable amount of time. If a supercomputer can't solve your schedule perfectly, why on earth do you beat yourself up when you can't do it either?
The math tells us that good enough is often the only rational target. It tells us that making a trade-off isn't a failure, it's a necessity. It tells us that if you followed a good process, if you gathered the data, used the 37% rule, or prioritized correctly, and the outcome still went wrong, that's not your fault. That's just probability. So, stop trying to find the absolute best parking spot. Stop agonizing over the perfect restaurant. Stop trying to answer every email the second it comes in. The most rational thing you can do is relax. That brings us to the end of our deep dive into Algorithms to Live By. I hope these mental models help you navigate the chaos a little more smoothly. If you want to grab a copy of the book, and I highly recommend you do, there is so much math we didn't even touch on. The link is waiting for you in the description. And if you enjoyed this breakdown, make sure to subscribe to The Last Read. We've got plenty more books to explore, and I'd love to have you with us for the next one. Thanks for listening, and until next time, happy computing.